In this second of 3 videos talking about how we deal with numbers in physics, we are going to talk about significant figures, sometimes called significant digits. So we're both going to talk about how do we identify how many sig figs that a number has, and also how do we do calculations with sig figs. So in the last video, we saw how to report numbers off of measurement devices, and that the number of digits that you report is important. So the number of digits that you report actually have a name. So we call those significant figures, or I like to call them sig figs. It's not quite as much of a mouthful. But the number of significant figures for a value is the number of digits whose values are known. So for this thermometer example, we know 4 digits. There's 4 significant figures here. Okay, here we reported 6 digits purposely. So there's 6 significant figures associated with this number. When first learning sig figs, it's almost easiest just to kind of jump in and look at some examples. So let's go ahead and look at the example 0.0500 kilometers. Okay, well, we know that this 5, definitely a non-zero number, is going to be significant. Okay, the first 2 zeros, however, are just placeholders, so those are not going to be significant. However, you didn't have to put those zeros on the right, so you could have wrote 0.05, right? If those other 2 zeros weren't significant, so they must be significant. So there must be a reason that those zeros were reported. So when we're looking at that first number right here, the 0.0500, there's 3 significant figures in that number. Okay, and looking at these first 2, you might have a question as to why are those not significant? Well, you can think about it. We could rewrite this number as 50.0 meters. Okay, you wouldn't write those zeros out front there. They're not significant. They're just placeholders. They're important in determining like what the number is, but they're just placeholders. They're not a significant digit. Okay, so that's our first example. Okay, the next example, let's say 1.62 meters. Okay, in any number that does not have any zeros, all of the non-zero numbers are always significant. So that second example has 3 significant figures. Okay, let's look at 330. Okay, well, this becomes a little bit ambiguous. Definitely the 2 non-zero numbers are significant. So we got 3 and 3. Okay, that 0 is not telling us much. It could be 330, or it could be that we didn't know this next digit and this is just a placeholder. Okay, so it's really not good to write numbers with these zeros at the end with no decimal. It's ambiguous, right? If we had to decide, I would say that this is 2 significant figures. Okay, what would be better, if you wanted to show that 0 was significant, you could put a dot there. Okay, if you did put a dot there, then that would turn this from 2 significant figures. If you have the dot, then it would be 3 significant figures. Okay, and to avoid ambiguity, you could write it in scientific notation and say it's 3.30 times 10 to the 2 liters. Okay, and then you also have those 3 significant figures. That one would also show that it's 3. You have the decimal point. That 0 is significant. Okay, looking at another example. Let's look at the example 7.0001 milliliters. Okay, in this example, well, we have the 7 and 1 are definitely not 0, so they're significant. Any zeros between 2 non-zero numbers are always significant. Okay, so that number there is going to have 5 significant figures or significant digits. Okay, let's do one more example. Let's do another kind of ambiguous. So let's say the number was reported as 48,000 milligrams. Okay, again, when you report it like this way, it's not a good way to report it, because who knows where in here. Let's say you actually knew that these 4 were significant, but that last one is not. Then this is a poor way to report that number. As written right here, that would have 2 significant figures if you had to make a decision. Okay, but what would be better and I'm going to scroll down a little bit here. What would be better is to report this in scientific notation. So let's say you did have all 4 of those. You wanted to convey that all 4 of those were significant digits. Well, if you put it in scientific notation, 4.800 times 10 to the 4th, then you can clearly see that all 4 of those are significant digits. Okay? And in scientific notation too, you could clearly show if it just is 2 significant digits. You could clearly show by just putting 4.8. So that would be 2 significant figures. Okay, so now that we've done some examples, I'm going to give you 3 rules to help you determine any number, how many sig figs it has. Okay, so the first rule is going to be that all non-digits are always significant. Okay, and that's kind of a given, but if it's not 0, it's significant. So 27.68 has 4 sig figs. 7.9 times 10 to the 6 has 2 sig figs. So just that 7 and the 9, the times 10 to the 6 is just showing the order of magnitude for that number. Okay, second rule, any zeros between 2 significant digits are significant. So I call this kind of the sandwich rule. So if you have a 0 between 2 non-zero numbers, then it's significant. Okay, and you count it. So 208 has 1, 2, 3 significant figures. 7.9046, that 0 is between the 9 and the 4, so it's significant, and this number has 5 sig figs. Okay, the last rule deals with zeros that are not in the middle, that are on the ends. Okay, and the rule states that trailing zeros, so the zeros on the right side of the number, are only significant if there is a decimal point in the number. Okay, so let's give some examples of these. So if we have 540.00, that number is going to have 5 sig figs. Okay, here 0.03040, these zeros out front are not trailing zeros. They're on the left side. Trailing zeros are the numbers on the right side. So this is our one trailing zero that we have, and there is a decimal point, so we do count it. So this number right here is 1, 2, 3, 4 sig figs. Okay, this last number down here, okay, that one is one of those ambiguous numbers that have been poorly reported. Okay, so if you write 23,000, that number has 2 sig figs, if you write it that way. And maybe that's what you were trying to report, but it's kind of ambiguous. In a number like that, you would probably want to write it in scientific notation to kind of show where the significance ends. So you will notice I didn't say anything about zeros on the left, and that's because leading zeros are never significant. So the only time this really comes into play is in numbers like this one, where you have a decimal, okay? And those zeros out, even if it's after the decimal point, if it's before any non-zero number, it is not significant. It is just a placeholder. Okay, and this is not really a rule, but an important note that writing numbers in scientific notation make it easier to determine the number of sig figs. Okay, so now that we know how to identify how many sig figs there are in a measured value, we're going to talk about what you do when you're combining these numbers together to do some sort of physics calculation. And we're going to start by talking about what do you do when you multiply and divide numbers. And that's a little bit more straightforward than when you add and subtract, so that's why we're starting with that one. So when you multiply or divide, the resulting value that you report should be reported with the same number of sig figs as the input number with the fewest sig figs. Okay, so again, probably easiest to show you with some examples. Okay, so heading back to our notes page here, let's go ahead and talk about what we do when we multiply together two numbers with a certain amount of sig figs. Okay, so let's say that we were trying to find that's a terrible M. Let's say we're trying to find the mass of an object and we know its density and its volume. So we're going to try to take a density of 4.05 times 10 to the 3 grams per liter. Let's say grams per liter. And multiply it by the volume of that liquid, that's 2.0 liters. Okay, so when we calculate that mass,
we take 4.05 times 10 to the 3 grams per liter, and we multiply it by 2.0 liters, okay?
And when we look at the sig figs, we're multiplying a number with 3 sig figs by a number with 2 sig figs. So this has 3 sig figs, this just has 2 sig figs. Okay, so when we multiply these together, and like our calculator would give us a number of 8.10 times 10 to the 3 grams, right? But we cannot report our answer with more sig figs than the one that went, than the input with the least sig figs. So we had 2 sig figs over here with our 2.0 liters, which means that I must report this as 8.1 times 10 to the 3 grams. Okay, so this needs to match, the sig figs need to match the one that has the fewest when you're multiplying. Okay, the same rule applies when you are dividing. Okay, so let's say for the second example, we want to find the velocity of a ball that's rolling on the ground, and we notice that it has a displacement of 9.0306 meters. We're able to measure that. And the amount of time that took was 3 seconds. Okay, and unfortunately, our stopwatch did not give us more than 1 sig fig. Okay, it's a poorly designed stopwatch there. Okay, usually you get at least to the 10th place. But when we're calculating the velocity, we take
9.0306 in meters divided by the 3 seconds to give us a velocity in meters per second.
And our calculator value, that either, you can do that in your head pretty easily, but a calculator would spit out 3.0102, right? But you got to be careful. That's not your answer that you can report. We only have 1 sig fig here. It's a terrible one. 1 sig fig. Whereas this one had 5 sig figs. But we're limited by this 1 sig fig. So I can only report that I know that that ball was rolling at 3 meters per second. So that's what I report. Okay, so our rule for multiplying and dividing is that you have to report your answer with the same number of sig figs as the input with the least amount of sig figs. Okay, so now that we know how we deal with numbers when we're how we deal with sig figs when we're multiplying and dividing, let's talk about adding and subtracting. Okay, so when you're adding and subtracting, you need to make sure that your input numbers are all having the same units, that they're written in scientific notation with the same exponent, and then you can do your addition and subtraction. But you have to accomplish those 2 things first, or you're not going to successfully be able to add or subtract them. So when your inputs have the same units and they're in scientific notation with the same exponent, the resulting value that you report should have the same number of digits to the right of the decimal point as the input number with the fewest digits to the right of the decimal point. Okay, again, that's kind of wordy. It's probably easiest just to kind of look at some examples, and you guys will see what I mean. Okay, again, coming back to our note sheet, let's talk about adding and subtracting numbers with tracking sig figs. Okay, so let's say that we were going to add 2 times together, and the 2 times we were going to add together 3.891 times 10 to the negative 6 seconds plus 0.0000452 seconds. Okay, so the first thing we notice, they're both in the same units, which is awesome, but they're not both with the same power of 10. Okay, this one's 10 to the negative 6. If we were to write the power of 10 here, usually don't write this. 10 to the 0 is just 1. So that would be 10 to the 0 as written would be the power of 10 that it is in. So we need to change this to a power of times 10 to the negative 6. Okay, so to do that, we're going to count 1, 2, 3, 4, 5, 6. So that is 5.2 times 10 to the negative 6 seconds. And we're going to want to add that to our value up here. Okay, so if you're doing this, especially if you do it out longhand, which you might not do very often, but let's just kind of show it because if you line it up and you draw a line, it's kind of nice to be able to visually see where you should round. So we have 3.891, and our powers are 10. We know our answer is going to be times 10 to the negative 6 because we've changed both of them to times 10 to the negative 6 now. And then I'm going to add to that 45.2. Okay. So when I do that, I got 1, 9, 9, 4. Okay, so I want to round so that I'm not reporting past here. Okay, so right here, this 45.2, that is, this only has one number to the right of the decimal point. Okay, so that's where I have to round, because this one has 3, but this one has the fewest to the right of the decimal point. Okay, so I'm gonna stop the number here, but my next number's a 9. So just like you would in math, you're gonna round. If it's a 5 and above, you're gonna round up. If it's 4 or below, you're gonna stay the same. Okay. So this becomes 49.1 times 10 to the negative 6 seconds. You can't forget to tack on that times 10 to the negative 6. Okay. That could alternatively be reported as 49.1 microseconds, right? Not a very long time. Okay, so that's adding two things together, and subtracting two numbers, looks very similar. Okay, so let's say we were going to subtract 5001 meters minus 40 centimeters. Okay. So, well, we're not even in the same units to begin with here. So I got to get these in the same units. So I'm going to change 40 centimeters to 0.4 meters. Okay, so now my problem turns into 45001 meter minus 0.4 meters. Okay. Okay, the other thing to think about, am I in the same power of 10 for scientific notation? When I write it like this, I actually am. I could have times 10 to the 0 times 10 to the 0. Okay. So let's go right into our subtraction. We got 45001 minus. Okay. So when we do that subtraction, what we end up getting is 45000.6. Okay. But looking here, so this had a decimal there. It doesn't even have one number past the decimal. So we're actually going to have to round here in the ones place. So this is where we round. That's a 6, so that rounds up. So we end up, that was such a small value compared to what our Sig Figs were for the 45,001 meters, that it actually doesn't change our value at all. Okay, so now we've been through identifying the number of significant figures in a number, in a value. Okay, we've been through how do you deal with Sig Figs in calculations, both when we multiply and divide and when we add and subtract. Okay, so again, the reason for this is that determining and tracking significant figures or Sig Figs in calculations prevents you from misreporting the precision of a value. Okay, that's all I have for you in this video. Thanks for watching.